the previous class, we discussed the virtual displacement because it's a very important idea, and then we introduced the first form of the foundation of the Lagrangian formalism, D'Alembert's principle. And D'Alembert's principle, as we discussed, it's a differential principle. So where instantaneous state of the system, using instantaneous state of the system with a small virtual displacement allows us to get the equation of motion. Pretty much using that, you should be able to pretty much know everything about the system. Differential principle. So today, and of course using that differential principle, we derived sort of like a general form of the Lagrange equation, right? So I wrote it down. So now the major player in this game is the kinetic energy. Of course, written in generalized coordinates. So now all these coordinates, QJs, are linearly independent, right? We call them generalized coordinates, right? And also, while we're deriving this, we introduced what is called a generalized force. So where we have summation over the whole system and the dot products between forces and that partial derivative of the r Cartesian coordinates, q generalized coordinates, of that partial derivative of those coordinates versus those coordinates, old versus new, right? So generalized force. Then, strictly speaking, you remember we started deriving that and derived for a system with constraints. And that's where the trouble was, because R's were no longer a set of linearly independent coordinates. So that's why we switched from R's to Q's. Okay, so strictly speaking, we should say, okay, that's only valid for a system with constraints. But of course, you all understand that if you remove constraints, that equation should be still valid. So that equation is valid for both systems, with constraints or without constraints. Right. And also very important thing which I need to emphasize on, that we haven't imposed any restrictions on those forces. Okay, of course, this is generalized force, but inside of generalized force, there is our normal force. Okay, not normal, I should be careful, actual forces. By actual forces, we mean all forces except for forces of constraints. And of course, the logical question should be, then where are those forces of constraints if we are not including them in this F? All those forces of constraints are in the transformation equations when we were moving from those R's to these Q's. You remember we wrote transformation equations, and how can you write those transformation equations? You will draw the picture, there will be some surfaces, maybe some chords or maybe rods. And using that geometry, using those basically constraints, we can write that transformation equation. So all forces of constraints are in the transition from the old coordinates, linearly dependent, to a new set of generalized coordinates which are linearly independent. Okay, so that's what we've done in the previous class and achieved in the previous class. Sort of. Now I quickly summarized. And now the next logical step. What if we, in this picture, look at the system, at the conservative system, right? And of course, in an attempt sort of to make that equation look better, look simpler. And I just want to get the typical Lagrange equation. So let's reduce ourselves to a conservative system. Basically, a conservative system it's a system where all forces are conservative, right? Okay, so now let's just get a typical Lagrange equation from the D'Alembert's principle. And then, of course, we will move to the Hamilton's principle. So let me check if I mention everything. Yeah, and of course, I should also emphasize so that kinetic energy now should be a function of what? All these generalized coordinates, right? And small number of generalized coordinates and capital number of particles in the system. And of course, it can also, not of course, of course, it must depend also on generalized velocities. Generalized coordinates, yeah, it can depend, it can not depend. But of course, kinetic energy must depend on velocities. Right. So, yes. Yeah, I mentioned all that. And so now, conservative system. Let's apply it for a conservative system. For a conservative system. Of course, you remember, conservative system. In a conservative system, all forces are derivable from potential energy. And potential energy should be a function of coordinates only. In a conservative system, potential energy is a function of coordinates. There are, of course, different type of system, like a monogenic, where potential energy can be a function of generalized coordinates and generalized velocities. But we're not going to discuss that. We're going to restrict ourselves to a conservative system. And of course, all forces can be derived Fi equals to negative gradient, okay, with respect to I. Basically, it's a gradient taking with respect to the coordinates on which this force is acting. So that subscript, basically, it means that here it's a delta sub Ri. And the potential, which is the function of, yeah, as I said, Q, yeah, Qi's. Wait, why no dots, no dots. Okay, coordinates only. All right, no, you know what, no, I shouldn't Q. Well, let's start with R's, right? So it's R, R1, and so on, Rn, right? Okay. Now, before I start plugging into there and then see what I can get for that generalized force, let me write explicitly all depend on what V depends, sort of explicitly, because then during that sort of short derivation, it's important to see all possible dependencies. Okay, so let me write it in this way. Because when you read the book, it might be difficult to see immediately. How did they make that transition at one point? Right, so of course, R1, so of course it depends on x1, which depends on all generalized coordinates. Then, of course, there will be y1, which depends also on all those generalized coordinates. And then, of course, z1, which depends also on all those generalized coordinates, right? Then, of course, there will be the same for x2, blah, blah, y2, blah, blah, z2. And then, of course, all the way to xn, yn, and z sub n. Okay, so that's, I wrote down explicitly all dependencies. Okay, and now let's start massaging generalized force. Right, so generalized force, Qj equals, so if we plug this minus gradient, of course minus will pop up, minus will be in front, and summation over the whole system, over all particles, gradient of V dotted with that partial derivative. Right. Okay, now let's write down explicitly gradient and these partial derivatives in order to get what we want. Okay, maybe I can squeeze over here, although I doubt. Okay, I will move to the next line, it's not a big deal. So partial derivative of V with respect to xi, right? X hat plus partial derivative with respect to yi, y hat, and plus partial derivative, of course, with z. Okay, z sub I, z hat. And that dotted with this. Again, let me write explicitly in a coordinate form. So it's a partial derivative of xi over qj x hat plus partial derivative with respect to qj y hat and plus partial derivative with respect to qj z hat. Okay, so now of course, and of course summation over I, all these i's we sweep over the whole set of coordinates. And of course, dot product is trivial. Of course, there will be only this term times this times that, and that times this. As a result, we will have minus summation over I and dv over dxi and dxi over dqj plus partial derivative of v with respect to yi and this with respect to qj and plus dv with respect to zi dzi with respect to qj. Now, what is this? We cannot just cancel those dx, dx. No. We need to look carefully. So what do we have here? It's a dv over dxi. Look at this explicit dependence. dv, okay, let me do dv over, look at dv, a partial derivative of v with respect to qj, for example. So qj, it's a particular q. Let's say q, I know, 3. And of course, this q3 is present everywhere, here, 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 in each of these sort of form of dependencies. Q is present is everywhere. So as a result, of course, we need to apply chain rule. So you will have, first, in order to extract q3 from here, it will be dv over dx1, right? And then dx1 over dq3. So in order to extract this dependence. Then, of course, there will be a dv over dy, and then, of course, partial derivative of y with respect to q3, giving us this term. Then, with respect to z, giving us this term. So pretty much, and then, of course, summation over I over here. So pretty much all these dependencies, two dependencies on this axis, present over here. All dependencies on qj in this column are in this term. And all dependencies on that qj over here is in that column. So pretty much what we have here is just a simple partial derivative of v with respect to this particular q, this qj. As simple as that. So instead of all this mess, I can just write down, okay, maybe I will move to the next line. It's a minus partial derivative of v with respect to qj. Right? So now we can replace this generalized force with this simple partial derivative. Again, if you take just a partial derivative with respect to qj, of course, you will get all these terms. Of course, massive number of terms. Okay, so now let me rewrite it here. Yeah, then I will move to that side probably. So partial derivative of t with respect to t out of t with respect to qj dot minus and equals to minus partial derivative of v with respect to qj. So that's modified. Now let's just make it look better. Pretty much at this point, yeah, we've changed it. What else do you want? Let's make it look better, more elegant, or maybe beautiful, right? So what we can do? We can just take this dv, move to that side, and combine with that term. Okay, so total derivative out of partial derivative, and you know what? Leave some space over here. And these two terms, of course, we can combine. This term goes to there with minus, oh, I mean with plus. So let me move minus. Okay, no, I said leave some space and didn't leave space for myself, right? So minus partial derivative of, with respect to q, j, and here we will have t minus v equals to 0, right? Then v, our potential energy, is a function of coordinates and, of course, generalized coordinates only. It doesn't depend on velocities, neither generalized velocities or regular velocity. There are no dynamic components in the potential. So as a result, we can safely add or subtract potential energy to that term. So we can add, subtract minus v and put a bracket. Because anyway, dv over dqj dot gives you 0. But in order to sort of simplify or make the form of this equation look better, we can do this. So now we have exactly the same construction, t minus v, in both of these terms. So it appears naturally, this construction, t minus v. So let's just give it a cool name. The Lagrangian function, or just simple, the Lagrangian. So in this case, you see the Lagrangian appears naturally, t minus v. Usually in the undergraduate course, I would say, let's just for fun consider this function out of the blue, t minus v, and call it Lagrangian. But from the D'Alembert's principle, it appears naturally. We don't have to say something, let's consider it for fun. Right, so now let's denote L, 3 lines, t minus v, and call it the Lagrangian. So basically, if you know a Lagrangian of the system, you can say you know everything about the system, because getting that everything about the system is just a question of time and some efforts, right? It's sort of like a Lagrangian. It's like a, I don't know, KGB file on a person, right? So if you open it, you can get any information about the person. Right? So let me frame it, because it's one of the most important. And so now let's rewrite in a typical form, Lagrange equation in a typical form. So it will be partial derivative of L with respect to Qj dot minus partial derivative of L with respect to Qj equals to 0. Usually whenever we talk about the Lagrangian, I use this wavy L. If it's a angular momentum, I usually use straight L. But of course, I will keep telling you about it. So let's frame it. And of course, this is a Lagrange equation. So, beauties of the Lagrange equation. First of all, yeah, it's a Lagrange equation. It's an equation of motion, right? So it allows us to describe motion of the system completely, right? And usually here we have what? N equation, probably I should also emphasize. So a J spans from 1 to N. One equation for each generalized coordinates, for that linearly independent set of coordinates. And beauties. First of all, major beauty of the Lagrange equation, that the form of the Lagrange equation doesn't change the form, the shape, right? If you move from one set of generalized coordinates to a different set. You just need to change coordinates. So instead of x dot and x over here, there will be r dot, or phi dot, theta dot theta, right? So you just change a variable and that's it. The form stays the same. And of course, the second major beauty, that you don't have to deal with vectors. Now it's all about energies, kinetic and potential. Right. So let me check if I mentioned everything. Yeah, probably I should mention that Lagrangian, it's a function of course, q, generalized coordinates, generalized velocities, and possible time dependence. Right. Of course, generalized coordinates only in v, but generalized coordinates and velocities can be in t, all right, in the kinetic energy. Okay, so let me check what else I need to mention. No, it looks like, yeah, next one. Lagrangian function is not unique. Even just by looking at the equation, you can tell, even if you just simply add a constant to the Lagrangian function, right? If you add here, for example, I don't know, 5, it will still satisfy the Lagrange equation, and you will still be able to get the same equation of motion of the system. But the freedom is even deeper, right? So if you, let's assume that L satisfies Lagrange equation and gives you equation of motion of a particular system. But if you construct a new Lagrangian where you just take the old one plus the total time derivative of some well-behaved function, the new Lagrangian would still satisfy the Lagrange equation. Let me write it down. And it's also in your homework, one of the problems. But you don't have to prove. I attached my solution. I just want you to go through that proof without wasting too much time. Okay, so let me write that down. So the Lagrangian is not unique. Okay, I'll put a new bullet. L is not unique. Is not unique. And so if L satisfies Lagrange equation, okay, describing a certain system, giving us an equation of motion, right? So then we can construct L prime, which is L plus the total time derivatives of some well-behaved function. Function can be of q, which subscript I use? Just the whole span. Function of generalized coordinates in time. But this function f, again, it should be good-looking, well-behaved function. What do I mean by well-behaved? It should be continuous, and you should be able to differentiate it as many times as you want or need. Right? So where f is a well-behaved function. Right. So then this L prime also satisfies the same Lagrange equations. It means it's a Lagrangian of the same system, giving us exactly the same trajectory. Right. So then L prime also satisfies Lagrange equations. Okay, so that can be written better. Okay, so we have freedom. Okay, probably let me underline this function not being unique. Okay, sort of. Again, as I said, it will be in your homework. You'll have to prove it. And the solution is attached, right? So let me look what else I've missed. Yes. So again, the beauty of Lagrangian formalism. Easy to deal with constraints. Constraints are only, you use constraints only to make a transition from R to Q's, and after that you can forget about them. And then you need to just write down the Lagrangian, and once you wrote down the Lagrangian, the rest, it's a straightforward procedure. You don't have to think. You just need to integrate and then differentiate, that's it. Just a pure calculus. thinking where thinking is not needed, right? All right. Okay, so now before we move to the Hamiltonian formalism, not Hamilton's principle, let's dive inside of the kinetic energy. Because yeah, as you see now, it's all about these kinetic and potential energies. Pretty much no troubles with potential energy, right? It just depends on the generalized coordinates only, but kinetic energy depends on generalized velocities and coordinates. And let's see what we can get in general, which terms we can get if we write kinetic energy in terms of generalized coordinates. Basically, I want to see if kinetic energy depends on when kinetic energy depends on generalized velocities linearly, or when there is a quadratic dependence, or when we have free terms. Basically, I just want to see a general form of kinetic energy written in terms of generalized coordinates. So let's just dive inside of kinetic energy, write it down, and in the future, we will need these results in 2 or 3 spots. I don't remember exactly. But from time to time, I will tell you guys. You remember in the first chapter, we saw general expression for the kinetic energy. Now, let's write that down, sort of preparing ourselves for future troubles. All right, so let me write some kind of short title, kinetic energy in generalized coordinates. Let me put a new bullet. So kinetic energy in generalized coordinates. And it's important in generalized coordinates because we know kinetic energy in Cartesian coordinates. It's just a 1/2 mv squared, where v velocity in just a regular Cartesian coordinates. But again, we need to make a transition to generalized coordinates, and we need to reveal all possible terms. Right. So, what? Probably I should say, of course, every time we make it, where is mine? We make a transition from Cartesian coordinates to generalized, right? And the transformation equation between them, let me write down. So it's Ri, a function of what? All q's, q1, qn, and possible time dependence. Okay, so that's what we're doing. And now let's see what happens to the kinetic energy. Because most of the time in every problem we will have to go through that. So total kinetic energy, again, you remember we still have that multi-particle system where we have n particles. So summation over all particles from 1 to n and 1/2 mi. Okay, let me write immediately dri over dt squared. All right. Okay, and now let's just differentiate that. Remembering, using this transformation equation. Of course, time dependence possible in each of these q's, and then explicit time dependence. So let's write down that. Right, so it will be summation over I, 1/2 mi. And now in the brackets, what we have, we need to introduce the new sum, summation. Okay, which subscript I use? Probably J. Yeah. J from 1 to n small. And so partial derivative of Ri with respect to Qj, and then Qj dot. And we need to take care of that possible explicit time dependence. All right. So it's a plus partial derivative of Ri with respect to t, and to the power of 2. Okay, so now let's just square it carefully with all this mess. And let me start with this term. Yeah. Basically, why? Because it doesn't have generalized velocities. That's why I want to start with that term. So it will be, and I want, yeah, I1n mi over 2 and partial derivative of ri with respect to t to the power of 2. So this term does not depend on generalized velocities. So it's a term free from generalized velocities. Now the next one, cross terms. And I want to keep summation over generalized coordinates outside and summation over the whole system inside. Okay, so it will be summation over j from 1 to n. Cross term gives us 2, and that factor of 2 gets cancelled. And okay, I will probably open the new bracket and use summation over the whole system. 1 over 2 will go, so we'll have just mi. Then product of those partial derivatives, so it's a dri over dqj, and times partial derivative of ri with respect to t. All right. All right, I combine all those, so now I need to close this bracket to conserve number of brackets opened and closed, and qj dot, linear dependence on generalized velocities. Okay, I hope I haven't lost anything. No, it looks like everything is good. And now we need to square that. So we're squaring the sum. Of course, we're going to get 2 sums, and we need to introduce the second different index of summation for the second sum. So plus, and again, now we'll have summation over generalized coordinates j and k. I will take those 2 sums outside. And summation over the system, I will again bring inside like I've done over here. So, and also 1 over 2, I also take outside. All right, so it will be summation over, not I, j and k, j and k, summation over generalized coordinates. Then 1 over 2, and mi, okay, I will take mi inside. 1 over 2 will be outside. Yeah, it's correct. And let me take now summation over the system. It's n capital, should be. Then mi. Again, I'm getting too close to the horizontal surface, and it's difficult to write. Right, so now this product of these generalized partial derivatives, dri over dqj, and partial derivative of ri with respect to qk. Again, as I said, we're going to change the index in the second sum. So this is j, it's that term, and then k from the second. That's it. Now I need to close this bracket and dependencies on generalized velocities. So it will be qj dot and qk dot. Whew. Open the brackets, this. So now I'll move to the top up here. So let me check, do I need anything? No. I can erase this. Okay, let me also quickly check if my camera is still recording. Yeah, it's good. It's just a new camera. I don't know exactly all, I don't know, how it behaves. So sometimes I'm checking it. So now let's denote, because it's kind of messy. So this first term, free from generalized velocity, so let's call it m sub 0. 0 because it's basically generalized velocity to the power of 0. Free term. Okay, so let's call it m sub 0. It's this term. Then linear term, which has a linear dependence. Again, all this mass, let's call it here summation over I, so subscript j will get out. So it will be, let's call it m sub j. So it will be plus m summation over j, summation over j from 1 to n, and mj qj dot term, which depends linearly on generalized velocities. And now the last one, again, all this construction in the bracket, I'm going to call it, now look, summation over I will take care of I, but we have subscript j and k. So outside, j and k will go outside. So let's call it mj sub jk. Still 1 over 2 over here. Probably I'll just move it outside completely, 1 over 2, yeah. Right, 1 over 2, then summation over j and k, double sum, m sub jk, and qj dot qk dot. Whew. We managed to get through this. Now we even can call, yeah, so this is sort of T naught, zero dependence on generalized velocity, plus T1, linear dependence on generalized velocity, and quadratic dependence plus T2, right? So we will need this from time to time. I don't want to rewrite what's the by definition mj, because you can see immediately. So that bracket, it's mj, this is mjk, just to save time. Right. So, yeah, as I said, we will need it several times. Now let's look at the special situation. Let me check if I mentioned everything. Yep, that's done. All right. Yeah. So now, special case. What if, and it happens quite often, what if this transformation equation doesn't have explicit time dependence? What does it usually mean in our life? If a system, transformation equation from Cartesian coordinates to generalized coordinates does not have explicit time dependence, it usually means that that system is isolated. So what do I mean by isolated? It means it's not exchanging energy with the outside world. So energy is not getting into the system and is not taking out of the system. We will look at a couple of examples quickly, just without deriving anything, right? For example, let's say you have, the example will be, let's say you have a hoop and there is a bead which can slide. And if you start spinning it, and if you write the Lagrange equation, okay, first transformation equations. The transformation equations are going to have time dependence. Why? Because you spin the system. Maybe there is a motor over here driving this hoop. As a result, immediately time dependence will be there. But if you just take a simple simple pendulum, okay, I don't have a simple pendulum, okay, something like this, right? And just let it oscillate. Transformation equations are not going to have time dependence. All right? So, because in this case, it doesn't sort of communicate in terms of energy with the outside world. So outside world is not affecting the motion of the system. But in case of the hoop, yeah, we were spinning it. As a result, time dependence appears explicitly usually. Okay, so now, anyway, so let's look at the case when there's no explicit time dependence. Again, explicit, it means that you should be able to see time somewhere in the transformation equation. Right, because all these generalized coordinates have time dependence, right? But we're talking about the explicit time dependence. So, a special case, which way I wrote it? Transformation equations are time independent. Okay, sounds good. All right, transformation equations. It's not just one, right? There are usually a few of them. Are time independent. Time independent. So basically, I can write, so R, which way I wrote it? Ri is not a function of time. Okay, so immediately, so what? Immediately we can write so that partial derivative of Ri with respect to time is 0. And now we can simplify all those factors m0, m1, m2. Okay, not m1, mj and mjk, right? So m0, there is a time partial derivative with respect to time. So if this is 0, m0 is 0. Easy. Better. So immediately m sub 0 equals to 0. Then mj, partial derivative with respect to time. If that is 0, bye-bye, right? And as a result, only this term survives because it doesn't have partial time derivative. All right. So as a result, we have only quadratic time dependence. Time proof. Kinetic energy has a quadratic term. All right. So there are no free terms, no linear terms, quadratic dependence on generalized velocities. That's what I wanted to say. Quadratic dependence on generalized velocities. Right. And of course, mjk is not 0. Right. So kinetic energy in this case, yeah, this particular special case we're going to address several times in this semester. I will tell you again. You remember, guys, we would have this situation then that there is no explicit time dependence, and immediately we would be able to write a quadratic term. So t naught, this is 0, t1 is 0, and only t2 will leave, right? So equals to t sub 2. So quadratic dependence. Dependence on q dot generalized velocities. Right. Okay, so it will be useful. Quadratic function of the generalized velocities. Okay, as I said, now let me quickly draw the system as an example, and transformation equations, and kinetic energies. Right. Those of you who were in my undergraduate level course, you remember this example because we spent the whole class solving it. The hoop with the bead. Examples. All right. So if you have a hoop, and okay, so let's say this is the axis, and it looks like soon I will have to change the marker. And let's say it's spinning with, okay, not this omega, small omega. Let me use small omega. Right. And some bead of mass m is capable of sliding without friction. Right? Because right now we're talking about this Lagrange equation where we're not supposed to have friction forces. Right, so, and this angle theta is used as a generalized coordinate. So, and in undergraduate level course we derived, so transformation equations look this way. So x equals r it's a radius, r sine theta times cosine omega t. You see, immediately explicit time dependence, x. It's the first transformation equation. Of course, for y would be very similar. R sine theta sine omega t. Again, explicit time dependence. And z equals to minus r cosine theta. Okay, let's emphasize. So we have explicit time dependencies. As a result, kinetic energy had this form. Let me look at my notes. mr squared divided by 2 theta dot squared. So it's a quadratic term in terms of generalized velocities. And plus what omega squared sine squared theta. And the term free from generalized velocities. It's this one, T1, T sub 0 or M sub 0. So for whatever reason, T1 is not there, right? So So explicit time dependence, and we have free term. But in a case, okay, so let me put the first number 1 and the second, just a simple regular pendulum. So this is the example of time-dependent system. Transformation equations time-dependent. So now simple pendulum. Right, so you have 2, 2, 2 ceiling, and you have simple pendulum M. Of course, the most convenient generalized coordinate is this one. So transformation equations, again, from Cartesian to this one, to this generalized. Of course, it's a trivial. X equals what? Length L, let's say. L cosine theta. Of course, where is that x? This is x. This is y. So L cosine and y equals L sine theta. So now you see there's no time dependence because that system was driven. This system is not driven. This system is sort of energetically isolated. And of course, immediately you can easily write down kinetic energy. Of course, you can make a transition, right? So you can start from Cartesian coordinates and then use transformation equation. You can easily get m over 2 L theta dot L squared. All right, so only quadratic term because, because there's no explicit time dependence. If there's no explicit time dependence, only quadratic term survives. That's what we have here. As a quick demonstration, without getting into details. Okay, awesome. So now, example. This time, yesterday, I decided, okay, I will skip it. We will have examples when we derive Lagrange equation from the Hamilton's principle, and then we will spend time. We will spend time looking at examples. Okay, so enough of D'Alembert's principle, which is the foundation of the Lagrangian formalism, and now let's move to the Hamilton's principle, which is considered quite often more elegant. And you know what? Yesterday I was sitting and thinking, right? I tend to agree with that because you will see the derivation of the Lagrange equation from the Hamilton's principle, right? And it's kind of, at least for me, it's more kind of smooth, nice, because if I compare it with the derivation from the D'Alembert's principle Lagrange equation, it's kind of like a running on rocks, kind of bumpy, right? Again, it's just an internal feeling, right, of that. So maybe that's why people call Hamilton's principle more elegant. And again, the major differences between these two principles, except that they're different, two different principles. The major difference is that D'Alembert's principle is a differential one, because you just need to know instantaneous state and small virtual displacement. But in the Hamilton's principle, in order to get the equation of motion, you need to consider the entire motion of the system, from the beginning to the end. You do something, you have to vary the path, right? But anyway, you need to consider the whole lifespan of the system. So that's why it's called integral principle. Hamilton's principle is an integral. D'Alembert is a differential. Small section of its life will allows you to get the equation of motion, allows you to get equation of motion. Okay, probably I will start erasing on this side so that I can start moving naturally from left to right. All right, because now I don't need this stuff. Now we're supposed to get this again, but from the different principle, Hamilton's principle. Okay, let me get some water.
Professor, I think you're muted.
Yes, sorry. Right? Because whenever I drink water, I mute myself so that you wouldn't listen my noises, right, natural. Right? And sometimes, a couple of times already it happened, I forgot to unmute myself. I was just telling that I need to get to the department to get a new eraser. This one is getting less and less efficient. So now it's a chapter 2. All right, so chapter 2, and probably I should say, yeah, Hamilton's principle. And then, of course, Lagrange equation. All right. You know, in the graduate level course, Hamilton is almost everywhere. Hamilton's principle, Hamilton's equations, Hamiltonian formalism, Hamilton-Jacobi theory, right? Hamilton equation, this, that, right? It's kind of sometimes feels like annoying. He was really depressingly productive. Hamilton's principle. Especially when we get to the Hamilton-Jacobi theory, there will be some, again, tons of equations with his name. Yeah, first of all, it's integral and more elegant. Maybe I should emphasize. It's a integral principle. Okay, you understand the meaning. I don't want to write that. And probably I will emphasize it's more elegant. Right, so then, yeah, I said it's you need to consider the entire motion. Okay, so now immediately, let's restrict ourselves, applicability of what we are going to derive, to conservative systems. I already mentioned 15 minutes ago that there are two kind of related type of systems. In monogenic system, potential energy can depend on generalized coordinates and generalized velocities. We're not going to discuss that. We're going to immediately restrict ourselves to conservative systems, where potential energy can be a function of generalized coordinates only. Sort of like a static function. There's no any dynamic, there are no any velocities, only position. Potential energy depends only on position, on the coordinates. Right, so let me write that down. All right. And again, we're talking about actual forces, no forces of constraints. You remember where forces of constraints all the time. They are all the time hidden inside here, inside of the transformation equations. That's one of the advantages of the Lagrangian formalism, that you don't have to keep track of them all the time. You just draw the picture, look at the geometry, all the forces of constraints are there, all those tensions, normal forces. Just using geometry, you write transformation equations and you can forget about them. And you only have to deal with actual forces. Actually, these are also actual, but that's how we call them, right? Okay, so, yeah, let me write consider. Consider a conservative system. So immediately we are restricting ourselves to conservative systems. I will emphasize on that. All right. And so it means that potential energy, not equal, just the potential energy, is the function of all generalized coordinates, right? And also no time dependence. Still, it's still possible if there is a time dependence, you can of forces, you can still introduce potential energy, but we're not going to get there. No way. All right. So now we introduce this, and so now, in order to move any further, we just need to state Hamilton's principle, because that's the foundation, which cannot be proved. I will try to justify somehow, but nevertheless, right? So before I can state Hamilton's principle, of course, we need to introduce the action or action integral, because it's an essential part of the Hamilton's principle. So let's denote, or not denote, introduce. All right, so let's introduce the action integral. Or sometimes just action. It sounds cool. The action integral as a functional, basically as an integral. All right, so we're going to use I, letter I, capital. It's an integral in time from initial moment of the system to the final moment, from the birth to death, right, of the system. All right, and L, Lagrangian. Now we just basically just solving the Lagrangian immediately. There in the D'Alabert's principle, it appeared naturally, right? L dt, and of course L Lagrangian, it's T minus V, kinetic energy minus potential energy. Okay, that's definitely should be framed, because it's an essential part of the Hamilton's principle, and now we are ready to write Hamilton's principle down. Right, so which I have three forms, probably I'll use these two. So first, the system travels along the path for which the action integral is stationary. So every time between initial point and the final point, system will choose the true path, correct path, and along that path, this action should be stationary. Again, stationary, it means it can be minimum, it can be maximum. We cannot say any more, any deeper, right? So just stationary. And you will see during the derivation why we can use only word stationary. But most of the time in our examples, the system will choose the path so that the action is minimized. Right? But of course, you can have a problem situations. For example, you want to increase, maximize the income of your company, right, of your business. Of course, you can set up the functional, and so you need to find the path to maximize the income, right, not minimize. Right? So it's possible situations, right? Of course, all this stuff is not applicable just for in physics. there are lots of more pragmatic applications of all these formulas, right, and ideas. So let me write that down first because it's a foundation. It's the axiom, right? So let me write. Okay, I will use blue. So this system. No, probably I should write Hamilton's principle again. So the system travels along the path for which the action is stationary. Is stationary. So it's one way of stating Hamilton's principle. So let me frame it. Or maybe in a class or so, we're going to use the second form of the Hamilton's principle when we're going to derive the method of Lagrange undetermined multipliers. So both of these forms of Hamilton's principle, they're basically the same, right? But written in a slightly different, stated slightly differently. Or if you vary this action along the true path, the variation should be 0. So let me state it. So the variation of the action is 0 along the true path. Okay, so let me write that down. All right, so the variation, it's a calculus of variation. You remember we have initial point, final point. All right, so the true path, and then you can slightly tweak it, right, move it around. Of course, keeping the endpoints fixed, right? So that's variation. So the variation of the action is 0 along the true path. Okay, and of course I can write it sort of delta I equals variation out of that integral, right? So from t1 to t2, L dt equals to 0. So that's the second form of the same Hamilton's principle. And of course, from both of them, we can get Lagrange equations. So now I will use this statement to derive that typical Lagrange equation. But when we get to the method of Lagrange undetermined multipliers, we will talk about that. We will use this principle just to demonstrate that both of them equally strong, right? Just right. Okay, so now before, let me look at the time. So we have 10 minutes. Okay, maybe we will be able just to start deriving Lagrange equation. But before I start deriving Lagrange equation from this principle, let me discuss what's the logic behind this Hamilton's principle. Kind of, it appeared out of nowhere. Why the hell the system would care about that action, trying to make it stationary or minimizing, right? So is the system completely crazy, right? So what's the logic, right? And I had tons of books in classical mechanics, and none of them even tries to justify, give some explanations. They just, okay, here the Hamilton's principle, now let's derive Lagrange equation. Okay, nice. All right, so maybe like after a year of thinking, I came up with this justification. Okay, and again, it's just mine. You can hate it maybe, but so far I haven't seen any other justifications, right? Look at the action. What are we minimizing? What do we have here? So it's a Lagrangian. It's basically T minus V. So we're looking at the difference between potential and kinetic energy. First, of course, over short period of time, and then we integrate. Basically, over the whole lifespan of the system, a system is trying to minimize the integrated difference between kinetic and potential energy. That's what system is doing. It's trying to find the path along which the integrated difference will be minimized. Again, kind of why. Okay, so now let's try to compare with life of some people. Let's, for example, let's consider a single person. Single person who, let's say, doesn't have any relatives, no kids, right, no parents, right, and no any social obligations, right? And so how would that person live his or her life? In terms of money. Of course, that person makes money, gains, right? And then, of course, spends money. And of course, since there is no one for whom that money can be left behind when that person will be gone, right? Of course, that person, of course, will try to make zero at the end, right? So if you make money, you want to spend them, have fun them, waste them, whatever, right? So, but to make zero at the end, right? Of course, in the ideal case. But of course, no one knows when it all can end, right? It can end right, instantaneously, right? So out of the blue, right? So of course, you cannot guarantee that you will make zero at the end. But at least that person will try to minimize the difference between making income and spendings, right? So now, effectively, system behaves in exactly the same way. If we compare potential energy, it's like making money, gaining potential energy, and kinetic energy, or this potential energy. And kinetic energy, it's like having fun, wasting money, right, spending money. So effectively, system, which is obviously doesn't have any relatives, no social obligations. So system tries to behave in exactly the same way. It's trying to minimize the income and spendings at the very end. But of course, in this case, it tries to minimize the difference, integrated difference between potential energy and kinetic energy. So system behaves like a normal egoistic person, right, who doesn't have any anyone to take care of at the end, right? So now we can say, yeah, Hamilton's principle is not completely crazy or bizarre. We can even use that to describe a person, a person's life. Of course, under certain assumptions, because now our lives, of course, is more complicated because of the connections. So that's how I justify Hamilton's principle. So after this, it sounds like not completely crazy, right? So after this, how much time? Okay, we still have 5 minutes. Awesome. Now let's at least start deriving Hamilton's principle. And strictly speaking, or not Hamilton's principle, Lagrange equation. Strictly speaking, we're not going to derive Lagrange equation immediately in this form. Again, we're going to derive Euler-Lagrange equation. I don't know why, but every book, they usually derive this more general equation, which is called Euler-Lagrange equation. And then you just slightly adjust it by just changing variables, right? And you can change the variables and make a transition to this typical Lagrange equation. So let's do the same. Let's follow the same pattern, because Euler-Lagrange equation more a general applicability, and then Lagrange equation, slightly more restricted. Where are my markers? I need to erase something. I will erase this. So let's, again, definitely the system will be again, conservative system, it will be later. Right now, we will just take a completely arbitrary functional, arbitrary system, and so on, because we just want to derive Euler-Lagrange equation, which I said has more general validity. So let me write the title. Euler. Okay, I heard different pronunciation of this last name, and so I decided to stick with Euler, right? Euler-Lagrange equation. All right, so let's assume that there is some system. Okay, maybe I will first start with, let's say we have coordinate y, x, and let's say some system. This is initial position of the system. This is final. Let's say this is x1, x2, this y1, y2, right? And there is some function over this field, right? So let's, which way I label it? F. Okay, so, all right, let f, which is a function of y dot and x, yeah, y dot and x, right? Defined in that space, right? And of course, acts on the system when it travels, right? Defined along the path. Defined, right, maybe right here, along. Okay, the path I will draw in a second. Right now, let me just state it. Then, all right, so let's introduce some arbitrary functional, right? The nature of that functional can be different, because again, as I said, applicability of this equation will be quite wide. That functional can describe, for example, the total travel time, or maybe the total distance, or maybe the total income, or maybe wasting of your time, right? Or potential energy, right? So it can be, number of problems can be, nature of the problems can be quite wide, right? So let's just write down in general, completely general functional, right? So now consider a functional. Functional, it's just a quantity written down in terms of an integral. And the major difference between functional and function is this. In a function, I know, y equals s, f as a function of x, right? In a function, inputs numbers. Let's say y as a function of x. You put numbers, x. X's inputs, and then as an outputs y, you will get also numbers. So numbers in, numbers out. But in a functional, inputs are functions. We'll see. All right. As inputs, you have functions. As an output, you will have number, because all these functionals, I will write in a second, it's a definite integrals. So of course, as an output, you will get number, maybe 5 meters. That's the shortest distance between 2 points, right? Okay, so that's the difference between function and functional. Right, consider a completely general functional, and which symbol I use? J. Okay, awesome. J, it's an integral from initial point to the final point. Okay, probably I should say not point, x1 and x2. Right. And, okay, that function f y dot x, it's an integrand, and dx. Okay, I should have over here stated another very important point. It's actually the first time when I see this. Maybe there are other books. Y dot in this case, it's a dy over dx. My explanation why Goldstein decided to use y dot, because when we derive Euler-Lagrange equation, it will be sort of easier to make a transition to time dependence. Instead of x dependence, we will have time dependence, and then that dot will be more natural over there. We will have, instead of dy over dx, we will have dy over dt. Right? So that's, I think, the logic. Right? So let me emphasize, so that y dot, by definition, it's a dy over dt. Okay, so that's the functional. And so basically, again, so what we need to find a tool, maybe some equation, right, which will allow us to find dependence y on x, basically the path, which is going to make this functional stationary, or minimize or maximize, again, stationary, right? Again, so the goal is to find some tool, some equation, which will allow us to find the path, the true path to the true love, right? So that functional will be stationary. Okay, so probably I will not be holding you any longer because basically we just started deriving. I wouldn't be able to finish. It would take probably like 15 minutes, only between 15 and 20 minutes, right, to derive this. Okay, so let's call it a day.